Hi, Peyton here. Heard you're looking for some help solving systems of equations using tables. Let me see if I can lend you a hand. The basic idea of this concept is to be able to look at a table of values and find where functions intersect. These are the solutions we're looking for. There are several other methods for solving this. We can use an algebraic method, we can use a graphic method, and then there's the numerical method, which is the way we're going to use, which is using a table of values. We're only concerned with the table of values part, but we're going to take a peek at the graphical part to give us a little bit of an edge when we do this. Here's the quick and easy approach to this. First thing we're going to do is we're going to take our calculator and we're going to input our equations on the y equals function here. Sometimes though we're going to have to solve an equation so that it's y equals. I'll show you in a second. The second thing we're going to do is look at the graph to get a general idea of where intersections may occur. And then our third step is to look at the table of values using the graph that we just looked at to get an idea of where this intersection is. Okie dokie? But we need a little bit of review before we jump into this. And let's first look at a system of equations that contain only linear functions. And there are three types of solutions here. There is first where there's only one solution, and this means that there's at one point where two lines intersect. Here's an example of that. One equation is modeled by the function y equals 3x plus 4, and the other is y equals negative x. Here's the graph over here to look at. We notice that there's a point of intersection at about negative 1, 1. And there's only one solution. We know those lines extend infinitely long. They stay straight. They don't bow back on themselves. They don't curve. They just stay straight. So there is only one solution. The second possibility is there are no solutions, and this only happens when two lines are parallel to each other. And another way of thinking of this is they have the same slope. Here's an example. One graph is modeled by y equals 2x plus 4, and the other graph is modeled by y equals 2x minus 3. And here's a graph of that. The two lines are running parallel. We can get a pretty general idea of that. We can tell that by looking at the lines. We know they extend infinitely. They're lines. They stay linear. They don't curve. They don't do anything crazy to us. We can also look at the slopes if we want to on our equations to make sure that they stay parallel. Then there's our third possibility of solutions with a linear system of equation, and that's where there are infinite solutions. And looking at that, you may be going, I don't believe you, I don't understand what that means. And this occurs when we have two lines that are exactly the same line, which means they sit right on top of each other. So at every point, they're the same. And here's an example of that, and both lines are modeled by the same equation, y equals 1/2 x minus 5. Here's the graph, and looking at the graph, it just looks like there's one line there, but there's actually two. We just can't distinguish which line is on top or not. But there's an infinite solutions. At every point, they're the same. Now, let's work some examples here. We have two equations. One is y equals 2x plus 4, and the second equation is 2y minus 4x is equal to negative 10. And here comes that little note I told you about earlier. We're going to have to solve the second equation so that it's y equals some function of x. And we're going to do that. So first thing we have 2y, excuse me, my pencil's not behaving with me, minus 4x equals negative 10. I'm going to add 4x to both sides to try to isolate y. So then I will have the equation 2y is equal to 4x minus 10. And I will divide both sides of the equation by 2. So then I will have y is equal to 2x minus 5. Okay? Now, since both equations are in y equals forms, we can punch them into our calculators. And we're going to do so by using the y equals buttons. So I'm going to do that right now. For the first equation, I'm going to type in 2x plus 4. And for the second equation, it's going to be the one we've solved for. It's going to be 2x minus 5. Okay? And your screen should look like this by now. Now, our second step is to look at the graphs. And let's take a quick look at that. And so here's what the graph looks like. And we're going to look to see if we can tell where a possible intersection occurs so we can find that on the table easier. And looking at this, it looks like the lines are running parallel to each other. It means there's probably no solutions, but let's look at a table anyways, and if we look at a table of values, you can scroll forever and ever and ever and ever and ever and ever until your heart is content with scrolling, and then you can scroll some more if you feel like it. You're never going to find where these two equations are equal to each other because the lines are parallel. Now let's look at another example. We have two equations. One is given as y equals negative x plus 4, and the second equation is y equals x minus 12. Fortunately for us, both of these equations are already y equals, so we can just punch those into our calculator right now. So my first equation will be negative x plus 4, and then my second equation will be x minus 12. Okay? Now let's take a peek at the graph to get an idea of where an intersection may occur. And so to do so, we'll just push the graph button and give my calculator a second. It wants to think. And looking at the graph, it looks like an intersection occurs at about the point x equals 8 and y equals negative 4. But to be sure, let's look at the table of values. And to do so, we'll push second, which is this yellow key up here at the top, and then we'll push the graph button again. And what will appear will be a table of values. Now we need to scroll down to where x equals 8. And that's where we thought the intersection occurs, and scrolling down, sure enough, we find that that's where the two equations are equal to. And so the solution to this system of equations is the coordinate point 8, negative 4. X equals 8, y equals negative 4. Okay? Here's one last linear system of equations example. We have two equations. One is y minus 3x is equal to negative 9. The second equation is a bit clunky, but it's y divided by 9 plus 1 is equal to 1/3 x. Now we can't plug these into our calculator straight off because they're not y equals, and we have to solve both of them. So for the first one, let's solve for y, and I switched to my blue pencil because my green one wasn't cooperating. So we have y is equal to 3x equals negative 9. Oh, excuse me, y minus 3x is equal to negative 9. And I'm going to add 3x to both sides. So I have y is equal to 3x minus 9. Okay, that does it for our first equation. Our second equation is y divided by 9 plus 1 is equal to 1/3 x. So let's solve for y. The first thing I will do is subtract 1 from both sides. So I will have y divided by 9 is equal to 1/3 x minus 1. Okay? And then to solve for y, to get it by itself, I will multiply both sides of the equation by 9. And in doing so, I will have y is equal to, okay, 9 times 1/3 will be 3, so it'll be 3x, and then negative 1 times 9 is negative 9. Okay? Now that both equations are in y equals form, we can put them into our calculator, and let's do so right now. So we'll push the y equals button. We'll have 3x minus, oops, not plus, I want minus, minus 9 as our first equation, and then our second equation is fishingly the same, 3x minus 9. We're going to look at the graph now. And looking at the graph, we see that there's just one line on our calculator. There's just one line. And looking at the equations, we could tell that they're the same equation. Let's look at a table of values now. So to do that, we'll push second graph on our calculator, and we can scroll and scroll and scroll and scroll and scroll. I have a screenshot right here for you. And scroll and scroll and scroll and scroll and scroll, and they will be equal at every x value. So we know that these two lines are the same, and therefore there's an infinite amount of solutions. Okay? That does it for linear equations.